Hello, my name is Joel Hinks, and today I'll be doing a presentation on the two fundamental principles of Kirchhoff's laws. So what is Kirchhoff's laws? Defined by German physicist Gustav Kirchhoff in 1845, Kirchhoff's circuit laws are applications of two fundamental conservation laws, the conservation of energy and the conservation of electric charge. As such, Kirchhoff's laws identify the relation of values of the current and voltage in the lumped element model of electric circuits. The two fundamental principles are Kirchhoff's current law and Kirchhoff's voltage law. Applications of Kirchhoff's laws. Both of these laws are widely used in the field of electrical engineering and are useful in understanding the transfer of energy through an electric circuit. Specifically, Kirchhoff's laws are applied in circuit analysis and circuit design, where it is necessary to determine the direction and value of current and voltage. In the case of Kirchhoff's first law, Kirchhoff's current law, also referred to as Kirchhoff's point rule, Kirchhoff's junction rule, or KCL, is a statement of conservation of electric charge. As such, this particular law characterizes and defines the way the electrical current is distributed when it passes through a junction or a point in a circuit where the charge has several possible paths to travel. Put simply, this definition means that the charge cannot build up at a junction and that the charge is conserved. From this, it can be said that at any node or junction in a circuit, the sum of currents flowing into that particular node is equal to the sum of currents exiting that node. Alternatively, Kirchhoff's current law suggests that the algebraic sum of all currents in a network of conductors meeting at a junction point must be equal to zero. This can be seen in the following problem. We see that L1 is the only current flowing into the node, and that there are three currents exiting the node. These are represented by L2, L3, and L4. Following the statement that the sum of all currents entering a node is equal to the sum of all currents exiting the node, L2 plus L3 plus L4 is equal to 1. Alternatively, bringing L1 to the left side, L2 plus L3 plus L4 minus L1 is equal to 0. This can be mathematically generalized as the sum of all currents at any particular junction point is equal to 0. I will now discuss Kirchhoff's second law. Kirchhoff's voltage law, also known as Kirchhoff's loop rule or KVL, describes the distribution of voltage or potential difference within any loop or closed conducting path of an electrical circuit. Specifically, Kirchhoff's voltage law states the algebraic sum of all voltage differences in any closed loop must equal 0. Kirchhoff's voltage law originates because the electrostatic field within an electrical circuit is based on the conservation of energy. And so, as you go around any closed loop, when you arrive back at the starting point, it has the same potential difference as it did when you began. As such, it can be said that the total amount of energy gained must be equal to the total amount of energy lost. Given this, Kirchhoff's voltage law can be applied when generating circuit plans, specifically for finding a value of voltage between any two nodes. This is demonstrated in the following simple problem. It should be noted that in any problem, if you encounter a voltage going from a higher potential to a lower potential, it is expressed as a positive value, and consequently, if it is going from a lower potential to a higher potential, it is expressed as a negative value. With this in mind, for this problem, we wish to solve and find the value of a proposed device V1. From the highlighted path, in a clockwise direction as indicated by the arrow, it can be seen that by implementing the Kirchhoff's voltage law statement, the total amount of energy gained must equal the total amount of energy lost. We get 4 volts plus V1 minus V10 is equal to 0. Therefore, using substitution, the value of the unknown V1 can be found. In this instance, V1 equals 6 volts. Now I will discuss the various limitations to the applications of Kirchhoff's laws. Both Kirchhoff's current and voltage laws depend on the lumped element model being applicable to the given circuit. This essentially means that the circuit under question makes a simplifying assumption that each element is fixed in space, and that the wires connecting the elements are perfect conductors. In addition to this, although Kirchhoff's laws are accurate with DC circuits, they only apply to AC circuits to instantaneous or complex values of currents and voltages. In the instance of alternating current, Kirchhoff's laws will never apply to RMS or root mean square values of currents and voltages. Thank you for watching. In this presentation, I've addressed the two fundamental principles of Kirchhoff's laws, their particular applications, as well as identified their limitations. I hope you now have a better understanding of Kirchhoff's laws.